So to give a quick review of the last lecture, eventually, this is for you to see how a discrete time functional block are different from analog functional blocks. And specifically, considered naturally, this brings the notion of mixed signal. And specifically, usually in analog, the terminology of analog is used when you deal with continuous time as well. So therefore, definitely in the literature, whenever somebody says analog, it's mainly continuous time. As soon as we move to discrete time, effectively everything becomes discrete time. And you notice when we discuss a circuit like a simple unity gain buffer, that discussion, analysis, operation, behavior is totally different from continuous time. And one of the reasons is because of the presence of switches, which have to give this kind of opportunity to the circuit to operate at different phases of the clock. And we deal with a clock, so therefore it is indeed a mixed signal domain. And therefore that's why the analysis is different. So we started with a kind of discrete time. dt means discrete time, unity gain buffer. And the entire operation was based on the sampling the input on a capacitor, put the capacitor around an op-amp, right? And then get the operation of a unity gain buffer, the same way it operates in the continuous time, but now it is discrete time. So creating a kind of dual correspondences between discrete time and continuous time, up to some limit you are familiar, because you know about now the Fourier transform in continuous time, you know about now FFT in discrete time, so you know at least, and Z transform. So at least from frequency domain analysis you have the background, but now we want to move to the circuits. So we give these examples, and then again I will be back to the signal processing domain to make a more kind of universal correspondence between the two domains. But you notice that for the analysis, we need really to assign, for example, what were the clock phases? One was eventually track phase or sampling phase, and that more often happens. In fact, in discrete time, always you need to have some kind of track or sampling phase. And then you have another phase. In track and hold, we call it hold phase, but here it's not just hold, it's more than that. It's eventually some operation. For example, it could be just a buffer operation, or say it could be amplification, or any kind of operation, say for example filtering. So we do this in analog domain. We want to do the same thing in discrete time domain. And the only thing right now we are not looking at is nonlinear operations. So first we talk about linear operations in analog domain. We take the correspondences in discrete time. Other operations, nonlinear operations, will be the topic of another subject. So therefore we are effectively looking at the linear operations, which is still a very important part of the operation available in mixed signal domain. So corresponding to the linear analog domain. And it's a part of eventually mixed signal processing, mixed signal domain processing. Okay, so this was exactly what we discussed last lecture. And we had these two phases effectively, and we had an op-amp. So they are all active circuits now. So that's why then we need to look at the bandwidth, we need to look at the speed, we need to look at the precision, the same way we were looking at the, in fact, let's call it speed. When we talk about the speed, naturally we are talking about unity gain of frequency, speed of the switches, settling time of the switches, settling time of the circuit. So always we need to look at this too, because this is discrete time, everything has to settle, every phase of the clock. And that's why we always look at this precision with respect to some corresponding LSB. This is the best way always to show, because this is, see, when we reach to LSB, eventually we are reaching to data converters, and this discrete time domain processing more often is a part of the domain which comes right before digital domain, and therefore it is better to just talk equivalent of LSB, which is very useful for making a universal unit for the precision. Okay, so now one thing which was very important last time was eventually to just considering a simple passive track and hold. The only difference was we were keeping the sampled input around an op-amp, and this is small signal analysis. You are talking about linear operations. So we had a circuit like that with an op-amp with a gain of A, assuming the unity gain of the op-amp is high enough. And what we consider as a generic case is that always there is an equivalent capacitance here, and this is something that is a kind of universal condition that you will see in many discrete time active circuits. That's why it's good to really know this circuit very well. When you know it, then you can apply it to many applications. And CL eventually is equivalent capacitance you see over here at the output node, which could be due to output capacitance of op-amp, input capacitance of the next stage, parasitic capacitance of C1 with respect to ground from this node, anything that you can imagine. Interconnect capacitances. So CL doesn't mean only load, equivalence. Similarly, Cin doesn't mean only input capacitance, anything which comes, even parasitic capacitance of the switch connected here, that will be also merged in Cin. So now you will have a generic case, and that's very interesting. Now we can work with this generic case and understand it. Okay, so as of now, I don't write A of S. I write only A. That means any limitation which comes from the capacitive loading around this at the frequency of operation, clock frequency of operation. The only thing was a slow rate of the op-amp, which was very important. And do you remember? If you remember, so there was a condition when at the beginning this capacitance was not around this op-amp at the beginning. It was connected to the input to sample the input, this phase. And then it was moved around the op-amp, or it was switched to the position around the op-amp using a switch. And because of that, and because of this capacitive loop, and considering Cin is not a very high capacitance, in fact, we will see Cin must be low. Otherwise, it will have a lot of impact on the everything, speed and precision both. So therefore, if Cin is low, most of the kind of abrupt change happens across Cin, which is at the input of the op-amp. And because of that, this op-amp will go to nonlinear region. And because it goes to the nonlinear region, therefore, we will have the problem of slowing. Therefore, a slow rate of the op-amp is important. And a slow rate is a nonlinear spec, because it happens only when the op-amp goes into nonlinear operation. That is the nonlinear aspect which naturally happens even though we are dealing with linear operations. I wanted to emphasize this. In this domain, because we are going with switching, Therefore, it happens that even linear element may get into nonlinear operation region, and we cannot ignore it. Therefore, that was the reason that some nonlinearities like slewing come to the picture. In fact, beginning of eventually this buffering phase was a nonlinear phase. When the op-amp was going into nonlinear domain, eventually because input of the op-amp eventually suddenly rises to a very high value differential. So input stage of the op-amp, one differential half circuit will be off, the other one will draw the entire tail current, and the circuit will get into a slowing mode. And after this slowing is settled, eventually the op-amp is going back gradually. This node again will go back to 0. Op-amp gets into linear operation, and then now the remaining phase will depend only on the speed of op-amp in the linear phase, linear domain or active domain. One thing also is that sometimes the slowing is the major reason for the delay or major contributor to the delay. This is also very important, but still we cannot have a limited gain or limited speed because that will have impact on the precision. So therefore, anyway, we need to have a proper op-amp. One important point is about the analysis. So last time I told you like, okay, this is a part of analog circuit and you have already done it because this is very similar to a common source amplifier with feedback capacitor. But I thought that I will give you an analysis today which is quite generic, and then you can derive it using the concepts without writing KVL KCL. This is not given in Razavi's book, but it may be helpful to you. First of all, because we have merged all parasitic capacitances between node B and ground by one capacitor, the input current eventually in this branch between node B and op-amp is 0. So therefore, it's a high impedance branch. No current flows here. So input impedance now is infinite. If you look from B, it puts C in aside. Now, if you look effectively, it's like if you look this way, you have C1 and you have Cin. So I draw it again here. So this is looking at, because the input current is 0, let me just temporarily remove this branch because it's as good as removing it. Of course, removing it will make this node float. But with respect to current, it will look like this. Now, what does that mean? That means that if you look, suppose there is something, some imaginary coupling which couples this node B to this node B dash. So we want to understand that how much is the voltage that we have here. This voltage actually is a fraction of output voltage and it's simply as capacitive division, because if you look from output, what this output will see a C1 series with C, right? Because this branch doesn't draw any current. Also, we see a kind of linear feedback. So, therefore, this circuit now, going back to the same circuit, can be considered as a feedback circuit. Fine. So, therefore, what is the feedback factor? Is C1 upon C1 plus C, which is eventually VB upon V out. This is feedback factor. However, don't forget there is a loading effect due to this feedback on the output node. This is not an ideal feedback. This is a feedback which creates loading on the output node due to feedback. So eventually this loading is C1 Cin upon C1 plus C, because it's a series capacitor combination. Fine. Therefore, we have a feedback circuit. We know the beta factor, feedback factor. We know the loading effect. And we know the equivalent circuit of the op-amp, which is for now doesn't have any internal capacitor and is simply modeled as what we had before. So I'm just showing the op-amp with the same nodes. That was the simplest version of this op-amp. Keep in mind, the input capacitance of op-amp, output capacitance of the op-amp are merged in CL and Cin. Therefore, the internal model is independent of frequency. Okay, and gain is very high. I mean, enough high. Okay, very high, not enough high. So therefore, GM around is quite high. We cannot make it low. Like if you make an op-amp with gain of 10, effectively we know it will not work. So you need definitely a gain above 100. That is the meaning of low and enough high. Fine. So therefore, this is a valid assumption that we can easily use it. Now, let's say we don't have feedback. That means beta factor is 0, right? So what is effectively the pole if beta equal to 0, but keep the loading effect? This is very important. I don't know if you have background in feedback system analysis, in linear feedback theory. When you want to analyze the feedback system, you need to consider first the loading effects. Loading effects are independent of the feedback factor. That means even if feedback factor is 0, loading effects remain. It's not an ideal feedback. In an ideal feedback, when you apply a feedback also is a kind of two-port system. You can have only one factor, like input voltage as function of output voltage, like put a voltage control current voltage source. But when you create a loading, this loading has impact on the what this module A could have generated if the feedback would have not been there. Therefore, it eventually changes the intrinsic behavior of A. That's why we keep the loading effect. That means what is now this condition? The equivalent circuit is this. This is only loading effect without any feedback factor. Fine. This is the model. And this is say V out. See, we have one pole at S equal to 0. So I told you, if you want to excite, you need to excite with the current source so that the model will not change. Right? We consider that. So that Cin eventually creates a pole at S equal to 0, which is not actually the concern right now. That is, anyway, is there. But there is one more pole, which is very easy to see here. It's just R out parallel to this capacitor, simple. Therefore, the main pole, not S equal to 0. So, main pole is 1 upon R out, of course, minus C1 C in C1 plus C. Okay, and if it is excited by input voltage source, even that S equal to 0 goes away, right? Because this node will be grounded when we don't have an input. So C in effect will go away. So this is the pole. Now, if we go back over here, we have actually the voltage feedback at the input. That means actually this input is a voltage source. That means C in effect already has gone in that analysis. So, but I made it current source to give you a kind of main view of the analysis. Now, fine, then we have the pole because we know that it's voltage excitation. So there is no effect of C in. So main pole will remain here only as the single pole in fact now. But effect of C in appears because C in has come to the loading effect. It's very interesting. C in affects the loading, but it doesn't appear as a part of the pole because when you excite this node with voltage, this effect of C in at this point will go away. The loading of the network, loading of the feedback network on the output node will remain. That's now you have this pole. This is without feedback, right? This is when I remove the feedback C1 here. So this is without feedback. So I have removed the feedback factor of C1. I have made it 0, but I have kept the loading of the C1, loading of C1 C in effect. So loading of the capacitive network or feedback network remains. Feedback factor of the feedback network is 0. So therefore, this is main pole without feedback, with loading effect. Now, if you look, if this is the feedback network, so and we have already the feedback factor, so therefore we have the loop gain. So loop gain is the voltage gain here, which is eventually, so let's call this pole P1. Let me make this absolute plus this way so that everything is positive. So loop gain now is eventually gain of the op-amp without feedback, which is GMRO. Multiply by feedback factor, which is C1 this is loop gain at low frequency. Let me write it at low frequency. And you know that from negative feedback theory, linear feedback theory, the pole after feedback is the low frequency loop gain multiplied by the pole before feedback. So therefore, all we need to do is just multiply. Of course, it is 1 plus loop gain, but because loop gain is very high, so it's almost 1 plus T. We usually show the loop gain with capital T. So 1 plus T is almost T. That's right, exactly based on the op-amp parameters. GM are out. Feedback factor. So T plus 1 is almost T because GMRO is pretty high. And in fact, if Cin ideally is 0, the feedback factor is 1. In fact, that is the ideal case of the unit gain buffer. So this is the T. Now, we just multiply by the pole. Now, pole was 1 upon absolute value R out multiplied by series combination of C1 and Cin. So, we write it over here, multiply by this term, GM R out multiply by C1 upon C1 plus Cin. And now you understand why R out didn't appear. Do you remember? Last lecture I wrote for you only GM. So R out doesn't appear. What does that mean? Means that if you increase R out, loop gain will increase. Main pole will reduce by the same factor. So therefore, it will not have any effect on the pole after feedback. And also, C1 plus Cin will get cancelled and you will get exactly the expression we had before. So if I simplify this, it will be equal to, so C1 plus Cin will get cancelled and then you will, maybe I write it here. And that is what we wrote last time. Did I miss anything? I missed the feedback. No, it's here. R out. Oh, I missed CL. See, you didn't tell me. See, something is missing. Okay, anyway, it doesn't matter. This is just CL. And then here we will have this term plus CL. Okay. Anywhere else I have to check? Yeah, here. Fine. Plus CL. Fine. Okay, now we simplify. So now you see C1 plus Cin will get cancelled. C1 is the feedback capacitor, will remain. Eventually it is GM multiplied by, now we will have, because of this Cin plus C1 and CL Cin C1, we will have all possible combination of 2 out of 3. And that is exactly the expression I wrote last time. So this way now it is independent of even what kind of amplifier it is, what configuration it has. And that's the way it tells you that what would be the, now the pole after having the feedback with loading effect included. Now this is very helpful because the parasitic capacitors we have, the main parasitic capacitor is Cin. Cl sometimes is out of our control because it anyways comes from next circuit, but we are designing op-amp, so we have to be careful to reduce the parasitic capacitance here. But of course, Cl also has effect anyway. So one thing which will be useful, and then I will follow in these expressions for similar circuits, all circuits. I write it in a form that you see in the form of relative values, not just this. This doesn't give you any idea with respect to design. When you want to design, it would be good to see the ratios. For example, we divide both numerator denominator by C1. Now what you will see will be Cin plus Cin multiplied by Cl upon C1. And then you will have Cl. So eventually, that means that, see, you can write it in two ways. You can write Cl multiplied by a factor, or you can write Cin multiplied by a factor. Both are fine. For example, if I write in the form of Cl multiply a factor, it becomes Cl, because Cl is something anyway will be there, though Cin also anyway will be there. I cannot make it 0. So divided by C1, so it will give me Cin upon C1. That means Cl is multiplied by this factor. That means the effect of Cl eventually is get enhanced by the ratio of Cin by C1. When you design, you want this effect to be low if you cannot reduce Cl beyond some value, below some value. And the other term would be, so we are including Cl, C1, and so this part is Cl, this part is Cin upon C1, and then Cin itself is. So Cin itself appears here. Cin upon C1 also increases effect of Cl. So it's a double effect of Cin. Cin appears as a parasitic capacitor. Cin upon C1 also increases the effect of Cl. That means we want to make sure that Cin upon C1 at least is low enough so that we have only effect of Cin and Cl, something like that, for the design purpose. Similarly, we will use these ratios, ratio form, which is very helpful for the design purpose. Here you don't get any idea how to design. Here you know how to design. Okay. So eventually, what is the meaning of that? Meaning of that is that if Cin is very low, that means the loading effect will go away. Only Cl will remain. That's the meaning of that, right? Only Cl will remain if Cin is close to 0. There is no loading effect, which is also true. Okay, suppose hypothetically I could have made this Cin 1 femtofarad something, and still get somehow that feedback factor. The problem is that to get that feedback factor, I need to have this ratio eventually maintained. Now, if you look at this, it is eventually 1 plus Cin upon C1. In fact, Cin upon C1 directly determines the feedback factor. But that is okay, because you can actually make Cin very low, therefore feedback factor approaches to 1. And that means that you will have the maximum bandwidth, which is fine. That's the ideal case, at least for the buffer. Okay. Is that clear? So I think this is now better because it's very generic. You don't need to do any detailed analysis. No KVL, KCL. There is, eventually I always tell the students, there is no learning in KVL, KCL. So therefore, don't use KVL, SCL at all, unless if you have to. And leave KVL, KCL to simulator. That is what simulator does. It blindly solves KVL, KCL equations. But simulator doesn't know what's happening and why. Right? So your difference is that you know why and what. Therefore, try to force yourself not to use it. I also try to do the same. That's why I try to find the techniques which helps us to use from what we know to derive. See, I use the basics of the linear feedback theory for single pole systems. If you have, say, H of S in general, say H0, 1 plus S upon P. If you apply it to a linear feedback system where the feedback factor also is independent, of frequency, say beta. The transfer function with feedback means that H beta of S after feedback That means low frequency gain will be divided by 1 plus T, and the single pole will be multiplied by 1 upon T. In fact, that is the reason more often people say that gain bandwidth product is constant. It's constant and applicable only to this case. Now, by changing the feedback factor. Now T, what is T? T is eventually H0 multiplied by beta. Low frequency gain multiplied by beta, which is independent of frequency. See, if beta becomes a function of frequency, then everything changes, because now this beta factor which appears itself will be a function of frequency. So that we have to derive. That's different. So the case we have actually is the case beta is not a function of frequency. So therefore we can apply this expression. So actually I use this expression. Okay, so we have almost finished the unity gain, discrete time unity gain buffer. One more thing which is left. By the way, there is one more name also for this circuit, which is called flip around discrete time unity gain buffer, because this actually does the flip around arrangement. So there was a switch for creating an analog buffer during sampling. There was another switch to connect it to the left plate of the C1 to create feedback, and there was finally one more switch for sampling or tracking phase. S1, S2, S3. So during the buffering time, which is also the whole time, so this actually gets flipped around op-amp. That's why it is called flip around buffer. That's it. That's just the name, in case you see that. Okay, and the sequence also we discussed. In fact, if we want to draw, so I thought it would be good to draw the signals control for the switches based on the arrangement we decided last time for reducing effect of charge area. I start from the time S2 turns off, because I explained it the same way. So this is logic high, this is logic low for the clock phases. This is for controlling S2. See, when first S2 turns off and then S1 turns off, and S3 is already off. Therefore, S1 will come a little later. The falling edge will come a little later. So this is for S1, same logic high, logic low. So there is a delay. Let's say here. So this kind of delay. In fact, if you see, the falling edge of the S2 starts before falling edge of S1. And that was the arrangement. We want to open S2 to avoid any high impedance path for charge injected from S1 into, to actually create, high impedance path for S1 charge which injected into S2. It will not be naturally high impedance because there is a Cin over here. And we have discussed that situation, if you remember, in the bottom plate switching case. And we showed that in the last lectures. With bottom plate switching, effect of charge injection completely goes away, even if it happens due to S1 here. And finally, S3. S3 and S1 are less or more similar. A little maybe, okay, this opposite because S3 is off. They're almost simultaneously. A little maybe the difference actually, but not much. So this is for S3. But S1 and S2 matter a lot. And this is created by adding some delay element. See, for example, if you make cascade of 2 inverters, that may give you a delay element. So that you can adjust the delay to give it exactly some delay. Make sure that, this is just to make sure that S1 is turning off when S2 is completely off. So this was about timing, just to show. Yeah, do you want me to talk about the charge injection cancellation in bottom plate switching here? If you want, I can repeat it here. After S2 is opened, S3 anyway is opened, you have this circuit. And I actually draw C in because telling C in is 0, I think is not it's not useful, because anyway it is there. So we have a C in, and so in fact C1, one plate anyway is fixed at the input and the other plate is connected to I put a voltage source, AC voltage source here, and this is S1, which is going to open, and S2 is already open. That's why I'm not showing S2 and S1. Charge injection in this case matters. Do you want me to analyze it for you, or you will do it? You analyze it. This is similar to the bottom plate switching that we already discussed. And I remember I made it in exactly very universal again in that case. If you have a high impedance node, in fact, it was in the DAC, CDAC in the SAR ADC. And based on that, eventually I made a generic case. See, this is also similar to that case. The only difference is that instead of comparator, we have an op-amp. Doesn't matter. All happens is that from DC point of view, this node is float. And any charge which is injected, the charge later will go to 0. See, right now some charge is injected. Say, let's say S1 gets opened, and some say, if it is NMOS, charge is negative. If it is PMOS, charge is positive, say NMOS. So some delta Q this way comes on these capacitors. Let's say as del V in is 0, because that doesn't matter really. It's not a part of this discussion. Say V in 0. So what matters right now, we want to talk about this charge, injected charge, not V in. See, say suppose this kind of charge comes. This charge on these two capacitors are equal because you have only one pad. And therefore, if you look at this node B, effectively on the left side, you have plus delta Q. On the other side, you have minus delta Q. That means summation of them is 0. Whenever you have this condition at the float point, what will happen is always it will remain the same. That's why as soon as you put this capacitor around this feedback loop, it can be shown that actually the final in the steady state, everything is 0. Okay, let me show you. Let's say we have this condition, right? We expect output to be 0. After we have S1 opened and S3 closed. So let's say we are moving to this state. And Vin was 0, small signal 0. So therefore we expect the voltage on C1 to be 0, which is not. So this is C1. Now, this was negative terminal, right? So which goes to the output. Therefore, now charge is this way, delta Q. And you can clearly see that, oh, it looks like we have an error. Delta Q creates a voltage. It should be 0 for Vn equal to 0. And here also is negative, delta Q, due to C, right? What would be steady state equations? So say in a steady state, A minus A multiply by minus delta Q upon CE. This is the input voltage, if this delta Q remains, which is the output voltage, right? Is equal to also summation of these two voltages, which is eventually minus delta Q upon C1 minus delta Q upon Cin. See, in a steady state, when op-amp has moved to the linear operation region, active, this expression is valid only if delta Q is 0. Therefore, naturally means that this charge will go away. Steady state equal to 0. This bottom plate switching is very, very useful technique. So therefore, you don't need really to design dummy switch, put them, so many things. As long as you take care of this bottom plate switching, so eventually see bottom plate of this capacitor, sorry, C1. Bottom plate of C1 is switching. So that's the meaning of that. Sorry, here is this side. Okay, this right side. I mean, if I show it per vertical, then it becomes bottom plate switching. If I show the capacitor vertical. Actually, when it is fabricated, also is vertical. In fact, we learned also how Cin is the problem for the speed of this circuit. So, eventually settling time gets affected. And of course, the slow rate is a very important factor. But still settling time is important because we want to be within a fraction of LSV, say within 1/8 LSV. So in precise designs, it matters. See, you know that now we have so many sources of error, mismatches, variations, noise. Therefore, we cannot afford that the sampling at the discrete time itself have so much error. One interesting point here is Cin is affecting the speed. So, we want to reduce Cin. Now look at the C1. Suppose C1 is a MIM capacitor. So this is say metal 1. This is say oxide. And this is, sorry, not metal 1. Say for example metal 3. And this is metal 2. Fine. And then below that we have again some oxide or field oxide. And then here we have the silicon substrate, say, or a well. So this is actually structure of C1. So if I want reduce Cin, I have two choices. See, suppose this metal 2 also has come out so that I can put contact on it, and this oxide also somewhere here gets terminated, but metal will come still out. How to show it? This metal still is continuing, and then here I take a stretch. So this is the metal. Show it with yellow color. See, this is the bottom terminal of the capacitor in this stack, and it has parasitic capacitance with respect to ground through this field oxide. So this is a part of Cin. If this terminal is connected, if M2 is connected, to eventually left side of C1. How to mention it? 2S1, eventually S1, switch S1. So therefore, to reduce effect of CE, when we actually do the layout, we connect the top plate. Sorry, this is node B, the other way around. If metal 2 is connected to node B. This is node B. So therefore, if I connect the bottom plate of C1, bottom plate eventually is metal 3, metal 2. Yeah, metal 2. So metal 2, I will have a parasitic capacitance to ground. Therefore, I put metal 2 here and metal 3 over there. That means top plate will be connected to node B. So therefore, this side is metal 3, this side is metal 2. Now Cin will come at the switch side and later will get absorbed in the Cl, and Cin will not be high due to that parasitic capacity. That's the one way of layout. Okay, so these are like some of the techniques during layout, because Cl usually already is high enough because of the next circuits. So therefore, it's important to at least reduce effect of Cin. Yeah, I think one more thing that we have not discussed is about precision. We talked about the speed, but we didn't talk about the effect of, I think, limited gain of op-amp. I think that part is limited. Let's list that have as well. The speed, of course, affects the precision, but it's not only speed. It's also the effect of gain of op-amp, that we have not discussed. Let's discuss that as well. So, and now we talk about the last part. This kind of analysis is unique for all the circuits. Speed analysis, effect of parasitic capacitors, charge injection, which is usually taken care by bottom plate sampling, and effect of op-amp gain. Okay, so then what should be the effect of op-amp gain? So we have actually, no, we don't have. Okay, so I draw it here. During operation, steady state, what is the circuit? The circuit is this circuit. I remove switches for simplicity. So this is C1 and this is Cin. And this is here. This analysis, of course, is straightforward. You can do it as well. So if gain is infinite, there will not be any error. If gain is not finite, then there will be error. I will write the final expression. It's just like, the same way in analog case. How do you analyze? So you don't consider this is a virtual ground, node B, right? So it's the same node B. So this is the discrete time equivalent of this circuit. Right? This, if you remember, it is A upon A plus 1 multiplied by V. Instead of 1, you will get that. How much error do you have? So it is 1 minus A upon A plus 1 multiplied by V, which will give you V in upon A plus 1. And if you want to get a relative error, so relative error means divided by V. 1 upon 1 plus A multiplied by 100. that usually we are not actually interested in relative error. Let's remove it because relative error doesn't have any position in this discussion. What we are interested is actually absolute error. We want always this V in upon A plus 1, absolute value, because these are all a small signal, to be less than some epsilon. Epsilon is a positive number. This is what we want always. When we go to discrete time, that epsilon is LSV upon 8, for example. LSV upon 6, LSV upon 5. So same goes here. In fact, you have this circuit now. Therefore, don't consider B is ground and actually analyze it. Same thing, eventually you consider you have a voltage VB over here, then VB multiplied by A will give you V out, and VB itself is the capacitive division of V out. You will get the V out as a function of V in. And V in is the voltage stored on the C1. Okay, so therefore if we write it this way, everything, yeah, and the voltage V in at the beginning is stored on C1. But at the end, it eventually gets also creates a voltage on the C in, which is not 0. So at the end, I will write the final. It's very actually similar to this case, but now we have the ratios as well. So eventually V out will be impact error. Let me write directly there. That's okay. Let me write V out, then you will get V1 is, sorry, V in into 1 minus 1 plus, interesting, this is also showing up, C in upon C1 upon A. This ratio of C in upon C1 is showing up here as well in the precision. So therefore, if when we say that we want this error to be within the limit, so effectively that means that this error, which is right now 1 plus C in upon C1 upon A, you want to be less than, say, LSB upon, say, 6. Right? This is therefore gives you an idea about the minimum gain of op-amp. So what does that mean? Means that if gain was very high, the entire charge which was stored on C1 during sampling due to V in would have remained on C1. But now because gain is limited, this voltage will not be 0. Therefore, some charge will go on C in, therefore charge on C1 will reduce, and effectively the output voltage overall will reduce. Okay, so therefore by having, that's very interesting, C in upon C1 is showing up everywhere. Input capacitance upon feedback capacitance. It's a very important parameter in the design. And interestingly, it appears almost everywhere because these circuits are very similar. All of them at the end of the day, you know, all these circuits are a kind of capacitive network in the feedback, a capacitive network at the input. That's why it continuously shows up the same way. Sometimes, because when you have a capacitive network on the left, so therefore, for example, you may have an overall equivalent cap, and that becomes parallel to C. It depends actually on the conditions. Sometimes also it's in series. I mean, yeah, at least in this case, we see that it appears as a ratio between C in and feedback cap only. Okay. Because in this type of circuit, actually we don't have any cap on the left in a steady state. The C in is a parasitic cap. Otherwise, there is no cap. But when we come to another circuit, for example, say a simple amplifier. Now we can talk about a little amplifier. So you know the inverting amplifier. This was an analog buffer. Now we have a simple linear inverting amplifier made of op-amp. So if I want to make counterpart of this in discrete time, one advantage of discrete time is there is no resistor. Therefore, one source of problems including variations, including a large area, power dissipation goes away. That's why discrete time circuits are so popular. They bring too many things together. Fine. What would be the element which we can replace instead of resistors to make a discrete time? If I want to make an inverting amplifier, op-amp will remain, of course, same with enough high unity gain bandwidth and gain. What we can replace if I want to get a gain? See, in discrete time, we have switches and capacitors and op-amps as of now, and comparators. So what we can use? Yeah, exactly. We had already a switch cap here, right? Why not to use it here? In fact, in a steady state, I can have this kind of circuit. If Vin is an AC signal, let's say, not DC, so gain of this circuit is C1 upon C2. Be careful, it's not C2 upon C1, it's C1 upon C2, right? If Vin is an AC signal. AC, small signal. So that's it. We replace them, but only difference is that you have to switch these capacitors, exactly. So therefore, it's a switch capacitor amplifier. So therefore, we move from that single capacitor case to the double capacitor, and that is what I was telling you. This C in, we'll see also a C1 on the left, and we'll see a C2 on the right. Okay. So then actually now, because you already know the entire analysis and the procedure, we don't again repeat each and everything for this case. We only repeat the important cases. In fact, this analysis also, you please do it. In fact, let me write here. So please analyze and derive. So it will be very useful. Okay, so then, okay, now I can remove this part. Now we have a pretty good idea about this effect of C-in. See, for example, Razavi has explained how charge injection effect gets cancelled or compensated and goes away, almost like one page, which is very nicely with details. My suggestion is that you first just analyze it the way we have analyzed in the class, using bottom plate sampling, generic and universal circuit. That's mainly analysis. It doesn't have any explanation, because with mathematical explanation, the derivation, like the way I showed you, derive it, delta Q equal to 0. Then you can read it. That's why I didn't follow exactly qualitatively explain and say that every kind of phase, what will happen now. So it's just a matter of drawing the circuit, showing delta Q and writing expressions. I think that would be easier for you to really see how it is. All you need to do is just repeat the analysis that we had in the class for yourself. Okay. Otherwise, circuits are given in the reference. So I'm trying to stick to the same circuit so that nothing will be new for you. Okay, so we moved now to the switched capacitor amplifier. I just give you one simple circuit, and then just we move to the discussion next week. By the way, you can make differential version, which is given in Razavi's book. I don't draw it. You can just make differential version of this circuit by giving the positive terminal exactly a copy of the same circuit. Then you will have a fully differential discrete time buffer. So that is not again required. Okay. So in fact, what we do, we derive it from this circuit that already we had. And I show it over here. So we already had C1 as a feedback capacitor for the unity gain buffer. In fact, let me show this part which is already there. And because we have two capacitors, I named it C2 based on the convention. And here we have a switch. Okay, this will remain same as before. The only difference is that we have a capacitor in the feedback, fixed in the feedback. Now, we had one capacitor also at the input, which was later getting switched. So instead of doing that, we add another capacitor, which will give us this C1 upon C2 configuration, exactly the way we want. So we keep this C2. The switch we had before around op-amp will remain. The switch we had connected to V-in will remain. See, this part is same as before. This part is same as before, this left side. C2 will be kept because we don't want again to bring C1 back. We need it at the input for the gain. So therefore, instead, we discharge it to ground. So this is now the switching version of the same amplifier. This was a steady state, right? A steady state is easily derived from analog counterpart. And this is the complete switched cap circuit. We added switches because we need to have a tracking phase. Here there is no tracking. So here is just an analog version of that with an AC analog signal, continuous time. We need to create discrete time, and for that we need to have tracking. That's why we need switches 1 and V. But we want to create a discrete time amplifier, and for that what we do is that we transfer the charge of C1 to C2. Therefore, effectively what we will see is the amplified version of input across C2 in the steady state. Means that in a steady state, actually this node is grounded and C1 is discharged to C2. That is the way discrete time works. Because we don't have the continuous flow of current in discrete time. We have to stop it. To do that, therefore we move the charge and store it on C2. So it's the same thing. So effectively it's like that to learn the concept. Suppose if you have a capacitor C2 and the charge stored on this capacitor, say C2, Q2, is equal to some, say for example, value of input. So therefore it is, say, C2 into voltage V. Okay, let's say V. Now we have another capacitor which has a, for example, charge of Q1 equal to C1 multiplied by V. We charge that capacitor by C1V. We charge this capacitor with C2V, say. And then we discharge this capacitor C1 into C2 in the same direction, so that this new Q becomes, say, C2V plus C1V. So that is equivalent by saying you have 1 plus C1 upon C2 into V. That is your amplification of V. So in discrete time, the basic principle is this way. This is one of the ways, of course. One of the ways. So effectively, we charge a capacitor, discharge it on another capacitor with a similar polarity. So we are increasing the charge across the same initial capacitor. So we are equivalent is, now we have amplified V to gain of, for example, K times of V when K is more than 1. So that's the whole concept actually behind this switching. In fact, here, exactly the same thing is being done. Okay. And in fact, if you keep they are equal, exactly equal, then actually gain will be 1. In fact, we can make also a unity gain transfer function in discrete time using this configuration rather than the other configuration. But this needs 2 capacitors.